Einstein's relativity has confused the general public generation after generation. This video explains why nobody truly understands relativity, and why relativity remains as a magic of nature. It also offers the mechanical approach for the first time to explain why the laws of nature remain the same for all moving frames. It is the key to unlock the mystery of relativity, a magnificent equality principle of nature at creating the universe. There are lots of books on relativity with stories of spaceships, trains, lasers, and moving light clocks and light rulers. However, people are still confused by the theory generation after generation. After reading a whole stack of those books, many of them don't understand why light can propagate in pure vacuum without any medium, why the speed of light is magically constant, why a moving clock is slower and a moving ruler is shorter, and most importantly, how could the laws of physics remain the same for all uniformly moving frames? The fundamental reason for that is because the mechanical explanation for relativity is missing so far. Without it, relativity remains as a magic of nature, hard to be understood by human brains. Furthermore, the constant speed of light should not be treated as the second key postulate of relativity. It is the biggest misconception in the theory, confusing almost everyone including Einstein. The principle of relativity holds true regardless of whether or not the speed of light is constant. It is not required to postulate that the speed of light is constant. In the real world, the photon never moves like a point object with a definite position at any given time instance. Instead, it moves like a wave without a definite position at any given time governed by quantum laws. The light clocks and rulers used in the classical relativity thought experiments never exist in reality. They only exist in our imaginations. Simply put, those thought experiments are wrong in terms of physical reality. With the same argument, the classical motion equation for light, c squared times t squared minus x squared equals 0, where the photon is treated as a classical point object, is also incorrect. It should not be used to derive the Lorentz transformation, a key transformation in relativity. The constant speed of light should be a hypothesis subject to experimental verification. Up to now, nobody is sure about the constancy of the speed of light. Neither the Maxwell's equations, nor the Michelson-Morley experiment can tell us the constancy of the speed of light because they are not exactly accurate. Recently, it has been found that spatially structured photons in free space travel slower than the speed of light. Vacuum isn't really empty, but is filled with virtual particles. A virtual particle pair can pop out of the vacuum for a very short time interval then disappear. Light will interact with those virtual particles. At present, nobody knows if the interaction with virtual particles in vacuum will slow down light from its maximum speed limit. It is postulated by the author that, at the most fundamental level of nature, everything is made of particle waves and field waves. All of those waves are different excited states of a fundamental medium, traditionally called the ether. Those waves, either free ones or coupled ones, are propagating in space with the same pattern defined by a quadratic partial differential operator g mu nu partial nu. Gravity is simply defined as variations of the wave propagation parameters g mu nu in space and time. As a result, the universal wave propagation operator g mu nu partial nu manifests itself as the space-time metric g underscore mu nu dx nu, where the covariant metric tensor g underscore mu nu is the inverse of the contravariant metric tensor g mu nu. Simply put, curved space and time are simply a manifestation of non-uniform propagation of particle waves. The variations of g mu nu are caused by the presence of matter and energy and other reasons such as the expansion of the universe. This is a mechanical explanation for gravity. At any point of space-time, the propagation operator g mu nu partial nu can be normalized to the standard form as -1 divided by c square partial t square plus partial r square and remains the same after the Lorentz transformation. That is exactly the reason why the laws of physics remain the same regardless of gravity, and the relative motion of an observer. This is a mechanical explanation for relativity. In particular, to any observer at his local space, every hydrogen atom, water molecule, protein, or any other atoms or molecules remain the same in their structures and properties regardless of the gravity and motion of the observer. Otherwise, life is impossible. When there is no gravity, it has been found in quantum mechanics that the propagation of particle waves and field waves are governed by the following operator. -1 divided by c squared times partial t square plus partial x square plus partial y square plus partial z square. This operator is oftentimes denoted as box, called the D'Alembert operator. In particular, for any free particle, either a boson or a fermion, it satisfies the Klein-Gordon equation as D'Alembert operator on the particle wave function psi xyzt equals m squared times c squared divided by h bar squared times the particle wave function psi xyzt. Here, m is the mass of the particle, c is a constant defining the maximum speed limit for all particles, and h bar is the reduced Planck constant, one of the most important constant in physics. There is a very important property for the universal wave propagation operator. It is invariant in form under the Lorentz transformation shown as follows. The original universal wave propagation operator. The Lorentz transformation applied to the space-time coordinates. The new universal wave propagation operator after the transformation with the new space-time coordinates. Note that it has the same form as the original one. Note that the Lorentz transformation is defined as x prime equals gamma times x minus v times t, y prime equals y, z prime equals z, and t prime equals gamma times t minus v divided by c squared times x, where gamma equals the inverse of the square root of 1 minus v squared divided by c squared, called the Lorentz factor. The Lorentz transformation defines a linear transformation from the space-time coordinates x, y, z and t of the original frame to the space-time coordinates x', y', z' and t' of a new frame. Note that the spatial origin of the new frame is v times t, 0, 0 in the original frame. That is, the new frame is moving with the constant velocity v with respect to the original one. The two frames are in relative motion with the velocity v. Invariance of the universal wave propagation operator under the Lorentz transformation is the actual cause for the principle of relativity to hold true in nature. It is a mechanical explanation for why the laws of physics remain the same for all uniformly moving frames. Inverse Lorentz transformation can be obtained simply by exchanging the space-time coordinates as x switches with x', y switches with y', z switches with z', and t switches with t', and replacing the velocity v by negative v because the two frames are moving in an opposite direction relative to each other. Specifically, we have x equals gamma times x' plus v times t', y equals y', z equals z', and t equals gamma times t' plus v divided by c squared times x'. As revealed before, in order to have the laws of physics remain the same, the space-time coordinates of the moving frame and those of the original one must satisfy the Lorentz transformation as a constraint. This has manifestations on the measurements related to space and time. The examples are relativistic speed addition law, the constant speed phenomenon, time dilation, length contraction, and loss of simultaneity. They are called the relativistic effects. When time and space are defined by the Lorentz transformation, the classical speed addition law, u equals u prime plus v, is no longer valid. Instead, it should be replaced by relativistic speed addition law. Assume that there is an object with its measured velocity in a moving frame as ux prime, uy prime, and uz prime. Then its velocity in the stationary frame can be discovered using the Lorentz transformation as follows. From the relativistic speed addition formula, we can understand the mystery of the constant speed of light. From the relativistic speed addition formula, it is straightforward to prove that if an object is moving at the speed limit c in one frame, then its measured speed in any other frames is always c. That solves the mystery of the constant speed of light. Specifically, if light is traveling at the speed limit, then its speed remains the same in all frames. Otherwise, if light is traveling at a speed less than the speed limit c, then the speed of light cannot be constant. From the formula, we can also see that c is the maximal speed limit for all particles in nature. No matter how long you add up speed for an object by acceleration, c is its maximal speed limit. Its speed can be arbitrarily close to the limit, but never reach the limit. Whenever we change the state of a clock from stationary to a steady motion, it appears to slow down in ticking rate. If we jump to the frame moving together with the clock, it restores the original ticking rate. This called time dilation. Time dilation can be derived mathematically from the Lorentz transformation. For a clock stationary in the second frame x prime, y prime, z prime, and t prime, let the elapsed time be delta t prime. Since it is stationary in it, we have delta x prime equals 0. From the inverse Lorentz transformation, we have delta t equals gamma times delta t prime plus v divided by c squared times delta x prime. It equals gamma times delta t prime. Since the Lorentz factor gamma is greater than 1 when the velocity v is not 0, we have delta t is greater than delta t prime. Time dilation is mutual. Assume there are two identical clocks in relative motion. Then to each clock, the other clock appears to run slower than itself. There is a key point at measuring length in relativity. To measure the length of a ruler, either stationary or moving, the key point is to take down the coordinates of the two endpoints of the ruler at the same time and subtract them to get the measured length. Whenever we change the state of a ruler from stationary to a steady motion, it appears to be shortened along the moving direction. If we jump to the frame moving together with the ruler, it restores the original length. This is called length contraction. Length contraction can also be derived mathematically from the Lorentz transformation. For a ruler stationary in the second frame x prime, y prime, z prime, and t prime, let its length along the x prime axis is delta x prime. Since we measure its length at the same time in the first frame, x, y, z, t, we have delta t equals 0. From the Lorentz transformation, we have delta x prime equals gamma times delta x minus v times delta t, that equals gamma times delta x. That leads to delta x equals delta x prime divided by gamma. Since the Lorentz factor gamma is greater than 1 when v is not 0, we have delta x less than delta x prime. Length contraction is also mutual. Assume there are two identical rulers in relative motion. Then to each ruler, the other ruler appears to be shorter than itself along the motion direction. The most important work on relativity theory has been done in history by Galileo, Newton, Michelson, Lorentz, Poincaré, Einstein, and Minkowski. There were also contributions by Voigt, Fitzgerald, and many others. This presentation is just an attempt to make it easier for the general public to understand the fascinating theory.